So in section 9.5, we're going to discuss population of two variants, or hypothesis test of two population variances. So section 9.5. We're going to be testing claims like standard deviation of one population equals the standard deviation of the other population, or we can test claims about their variances, which is a little bit more accurate in this case. One of the things that's going to be required of us in this section is that we get familiar with a new distribution. It's called an F distribution. Now, we've started out with the Z distribution in this course, which was nice because there was just one Z distribution, and that was it. Then we moved to the T distribution, and the challenge with the T distribution is that it changed with degrees of freedom. With the F distribution, you don't have just 1 degree of freedom, you have 2 degrees of freedom. So there's a lot to keep track of with the F distribution. Like all our other distributions, it has a total area underneath this curve of 1. Like the chi-square distribution, it starts at 0 and moves out towards infinity. It'll change with degrees of freedom. There's so-called numerator degrees of freedom and denominator degrees of freedom. So it has 2 degrees of freedom associated with each F distribution. That makes it a challenge. Can somebody move it away from the... I don't think the library wanted that back anyway, so... All right. Thank you. All right, so we got some entertainment today anyway, so that's good. All right, so numerator degrees of freedom and denominator degrees of freedom have to be specified for each F distribution. And because of that, your tables only work with areas that are in the right tail. So as to limit the amount of space we need to devote to this. You'll find these tables on page 728. And let's just practice and look up a couple values from this F distribution. So we'll start with looking up an F distribution with 5% of the area in the right tail. So remember, that always represents the area in the right tail, period, just like our Z and T scores. 4 and 12. This is not a particular number that's in the book. So again, this is your numerator degrees of freedom and denominator degrees of freedom. This is section 9.5. And I guess for 5% of the area in the right tail, I need you refer you to page 730, which has the tables with 5% of the area in the right tail. Across the top, you see numerator degrees of freedom. Down the side, you see denominator degrees of freedom for this specific area in the right tail. We want 4 across the top and 12 across the bottom. See if you can't find that particular F value. So what are you getting? Good. 3.2592, so 4 here and then down to 12. 3.2592. Let's try one more like that, and that'd be F with, again, 5% of the area in the right tail, 7 degrees of freedom in the numerator, 21 in the denominator. So 7 across the top, down to 21. What are you getting on this one? 2.4876. Now what we would do when we were kicking this old school is that you would set up a hypothesis test so that your area, your critical value was this point in the right tail. We would not set these up as a two-tail test. We would kind of work it so that it was a one-tail test. And what that would used to mean is you would have to contrive for the larger standard deviation or the larger variance to be in the numerator. That would effectively make it a right tail test. So you have to play around with the areas and think a little bit. If you take a careful look, your critical value here for the two-tail test is alpha over 2 in the right tail. For the one-tail test, it's just alpha. So here you are splitting it up, even though we wouldn't find this area in the left tail. The nice thing is that with Statistic, we don't have to worry about that. So we are going to continue to set things up and do our hypothesis test with a p-value. As far as kicking this one old school, the actual computation of the test statistic is pretty straightforward. It's just a ratio of these two variances. Each of these variances has a chi-square distribution, and the ratio of the two chi-square distributions gives you an F distribution, which is where we do our test. Now, one thing that's critical about this test is that your populations are normally distributed. So the two populations are normally distributed. This test is very sensitive to that requirement. With regard to that, let's take a look at, I think it's problem number 4 in the book. Students of the author randomly selected 217 cards and recorded their ages, and they randomly selected 151 faculty cards and recorded their ages. If, using the F-test with these data, is it correct to reason that there's no need to check for normality because N1 and N2 are greater than 30? So since we have a large sample size, we do not have to worry about normality. What do you think? Well, certainly in this case, the sample size or the mean of the ages of student cars and the age of faculty cars, that mean would be distributed normally. We're not making any test of a claim of the population mean. We're testing the population variances. So that these are normally distributed when N1 and N2 are greater than 30 doesn't matter. What matters is that the underlying populations, the populations that you're sampling from, have to be normally distributed. So it's not enough just to have a large sample size. Large sample size cures a lot of ills for us. It gets us to a normal distribution or something that's just approximately normal, and that's great. But large sample sizes in this particular case don't help. So the answer is no. Let's actually do this one, and I think that's reflected in problem number 6. So again, students of the author collected these, found that a mean age of 7.89 years, a standard deviation of 3.67 years. So, okay, we're going to have to hope that these are normally distributed. Let's take a look at Statistic for this. Let's set up our null and alternative hypothesis as usual. So let's finish reading the rest of this. Use the 0.05 significance level, or using the 0.05 significance level, is there sufficient evidence to support the claim that the ages of student cars vary more than the age of faculty cars? All right, I think we can do this one ourselves using Statistic, so let's give that a shot. Problem 6. Our null and alternative hypothesis. One of the things you're going to be faced with quite often in this class is the need to decide, well, gee, what parameter am I testing? So they didn't really say specifically. It says using a 0.05 significance level, is there evidence to support the claim that the ages of student cars vary more? So what parameter am I testing? Yeah, standard deviation, or what else could you say? Variance. Yeah, variance. So standard deviation or the variance. Now, technically speaking, the F-test does work with the variances. So let's just put the variances down here. Now, the original claim that we're testing is that the age of student cars vary more than the age of faculty cars. So I'm just going to write this as sigma squared sub student, or you can just write sigma squared of sub s is greater than sigma squared sub faculty. Now, if you just want to write sub s and sub f, that's fine too. I think it's getting at the same idea. It's just helping you remember, what's what. If that's my alternative hypothesis, what do I have to put in the null hypothesis? Yeah, variance of the students is less than or equal to variance of the faculty. Great. We're going to perform our test at the 5% significance level. Let's go find our p-value from this test and then make a decision. So we'll go over to Statistic, analysis, hypothesis testing. What looks promising at this point? Yeah, standard deviation, 2 samples. Let's plug in some values here. Sample size. Let's see. All right, so for students, we had 217 cars. They had a standard deviation of 3.67 years. For faculty, we had 152 cars, and they had a standard deviation of, 3.65 years? Wow, that's remarkably close. Oops, how about 3.65? Let's do 2 things. Let's first of all adjust the alternative hypothesis. So first population had a standard deviation greater than the second population, so effectively it's a right tail test, and then hit evaluate. So we get a p-value of 0.4745. P-value 0.4745. What's that suggesting about our hypothesis? Accept or reject, or fail to reject or reject? Good, fail to reject. Going back here, there was our original claim. Maybe I should have left all these things with you guys, but I think you have some of them as well. The original claim does not contain the possibility of equality, and we fail to reject that original claim. So there's not sufficient evidence to support the claim that the standard deviation of the age of student cars varies or is greater than that of faculty cars, or that there's more variation in their ages than that of faculty. So there's not sufficient evidence sample evidence to support the claim that the age of student cars varies more than the age of faculty cars. Okay, looks good. Let's try one more like this, and I'll give you a choice. We could do body temperatures of men and women or skull measurements. This is a kind of an anthropology study comparing skull measurements from skulls that are 4,000 years old, or actually 6,000 years old, to those that are much more recent. So, any favorites, 10 or 12? 12? All right, cool. Let's go with that one. Before I do that, I should ask, are we okay with 6? That one go right? All right. So the head of this campus used to teach anthropology, and used to enjoy discussing with him, so this would be something that he would be interested in telling me a lot about. Researchers measured skulls from different time periods in an attempt to determine whether inbreeding of cultures has occurred. Results are given below based on data from ancient races of Tibet. Use a 5% significance level test to claim that the variation of maximal skull breadths in 4000 BC is the same as the variation in 150 AD. So, okay. Another test of variation. You can set this up, your hypothesis, with standard deviation or the variance. But one way or another, we're going to see if these two things have the same variation or not. One thing you could look at, and perhaps should look at, kind of a little thing we're skirting around, is the distribution of these things. If we were doing problem number 10, we could pull up the data. We're not doing problem number 10, so we're going to have to assume that these are both coming from a normal distribution. So for problem number 12, H0, HA, we're testing the claim that the variation is the same for 4000 BC and 150 AD. So sigma sub 4000 BC equals sigma sub 150 AD. On the flip side of that, these would be different. Okay, we had number of skulls here, number of 4000 BC. We had 30 samples here, and that had a standard deviation of 5.13. And we had the same number in 150 AD, and S there was 5.35. Doesn't seem like a lot of difference there, does it? I mean, they seem somewhat close. I don't know. For myself, it doesn't look like there's much of a significant difference, but sometimes, you know, these differences do crop up. What we'll do then is we'll do a confidence interval afterwards. Make sure that our confidence interval matches our conclusion here. Let's go back to Statistic, put in some numbers. Sample size of 30, standard deviation of 5.13. Second sample size again was 30, Standard deviation of 5.35. There's one more thing I have to do before I hit the evaluate button. What is it? Change the hypothesis. We want not equal to as the alternative hypothesis. Just for something different, I'm going to hit the plot key. So, kicking it old school, what you would get is a critical value, and you want to see if your test statistic is bigger than that critical value. So, here's what they're drawing as our distribution. And since our critical value is just a little bit above 1, it's not to the right of this value. So you'd fail to reject. We should see a p-value that matches this. So let's click evaluate here. Is this p-value closer to reject, or is it like really, really fail to reject? Which one is it? Yeah, the latter one. This is far from conclusive evidence that these are different. Is that what we're seeing when we see this confidence interval for the ratio of the variances? Now, the ratio is a little bit closer to how you do the test and what we used to do when we were doing these things by hand. Oops, that's not the right one. There we go. So when we're doing these things by hand, a lot of times what we would do is we'd set up this ratio. The one that is expected to be higher, we'd put in the numerator. So 150/80 divided by variation for 4000 BC. But what's happening when I divide both sides by this thing on the right, 150/80, 150/80. I guess I should have done it the other way around. Divide both sides by 4000 BC. By 4000 BC. Can anyone simplify the left-hand side for me? Yeah, you're just going to get a 1 is equal to this ratio. So if you had something that was pretty extreme, this compared to this, what's going to happen is that this ratio is going to be much bigger than 1. If you look at our confidence interval, the way it's set up on StatDisk, our confidence interval is for the ratio of these two things. The important thing to see is that that interval contains the number 1. If it contains the number 1, then that means that these two variances or these two standard deviations could be equal. So this is consistent with the null hypothesis. Finishing this up, our p-value was 0.8226, and that's a huge fail to reject. Fail to reject H0. Now, our original claim in this particular one was that the variation of these things was the same. So that was our original claim. See if you can't state for yourself, take a moment to practice, what the conclusion should be. So, who wants to give this one a shot? What did you write for your conclusion? Meredith, thanks for volunteering.
I said there's not sufficient evidence to warrant rejection of the claim that the maximal skull breadth of 4,000 BC is the same as the variation in 1844.
Perfect. Beautiful. Even better than mine. So, you should be following this path. The original claim contained equality. Yes. Do we reject? No. So, there's not sufficient evidence to warrant the rejection of the claim, etc. And then you restated it beautifully. Thank you. Are we okay with problem 12 here and these kind of hypothesis tests? For homework, try problems 5 through 13.